So continuing with Voronoi diagrams from last time, um, we said that Voronoi diagrams store proximity information, and for every point in the plane, every point of the point set that you're given, it constructs the locus of points, the convex polygon, whose interior points are closer to that point than to any other point. Okay, and we mentioned that it captures a lot of problems where proximity information is important, and it covers a lot of ground. It works in different metrics, not just Euclidean. There's dynamic versions, and the dynamic versions allow points to move and still keep the Voronoi diagram maintained properly as points move, or even when points are inserted or deleted, as well as moving around. There's entire conferences on this subject, and a lot of art and architecture incorporates Voronoi diagram kind of motifs in it. It's very ubiquitous. Even nature has Voronoi diagram kind of structures, and for good reasons. You can read more about it, for extra credit, why that happens. We mentioned a term project idea for Voronoi art to maybe augment your TSP kind of art that maybe you're already working on, or just an alternate project. There's the Voronoi Mona Lisa, Voronoi cat, pretty cute. We said that the unbounded cells of a Voronoi diagram are associated with convex Hall points, so that gives you a nice association of convex Hall points and the Voronoi cells, which are the unbounded ones. So for free, essentially, you get the convex Hall. Nearest neighbors are across Voronoi diagram neighboring regions, and so that's an easy way of finding all nearest neighbors very quickly. It's a planar subdivision, so you can search a Voronoi diagram for point location, arbitrary point queries in logarithmic time based on planar subdivision search, which is the technique we showed a couple of weeks ago. And the dual, the graph dual of the Voronoi diagram is a Delaunay triangulation. Oh, that's better. So the Delaunay triangulation, basically you connect all points which have a neighboring Voronoi diagram cell border, a joint border, and it gives you a nice triangulation. It has a property that it minimizes, it maximizes the minimum angle over all possible triangulations. It could be an exponential number of those. And minimum spanning trees are a subset of the proximity diagram of the Delaunay triangulation, actually. And so we said there's a lot of problems, all of which require n log n lower bound, and they're all doable in n log n upper bound once you have the Voronoi diagram. So then the question is, how do you solve all these problems in optimal time? And the short answer is by obtaining the Voronoi diagram first. And so the question now reduces to how do you get the Voronoi diagram, and how do you do it quickly? So we'll start with kind of a simpler algorithm first. So to get the Voronoi diagram, you can use the fact that a Voronoi cell is the intersection of all the half planes, which are the perpendicular bisectors of pairs of points, one of them being the target point. Okay? And before we even do that, let's give a even simpler algorithm where the points are in a bitmap. So you have a big bitmap, and m by n, or say n by n large bitmap, say 1,000,000 by 1,000,000 pixels, or any number of pixels. And you want to find all the points that are closer to a given point than to any other point. So what you can do is expand wavefronts from all the points. Again, this is assuming it's a bitmap, which often it isn't, but we'll look at the other case, the more general case, in a minute. So starting at all the bits, which are the points that are given to you in the bitmap, start marking all the points by an expanding wavefront from each point. And when wavefronts meet, freeze the points there and stop the expansion process when two different wavefronts meet and crash into each other. Then freeze the expansion right there, but keep expanding everywhere else. And soon enough, you'll have the Voronoi regions kind of marked out in the bitmap. You keep marking the bits with the indices of the points where the wavefront started. It's possibly easier to see this in a color-coded way. So in a color-coded way, all the points with an expanding wave are marked with that particular color of the point that's where the wave started expanding from. And you get the Voronoi diagram pretty quickly. So this works nicely for bitmaps. How many get this approach? It's pretty straightforward. Just expanding wave fronts, and then when they collide, they freeze. Now, the issue is that the total time is the size of the bitmap itself. So if you have a million by million bitmap, which is a very large bitmap, the time will be 1,000,000 squared, roughly. I mean, just to initialize all the storage will take you that long. So it's roughly the size linear in the bitmap. On the bright side, it's independent of the number of points. So it doesn't matter how many points you have marked originally in the bitmap, the time will still be proportional to the size of the bitmap, independent of the number of points of the bitmap. So, and the other issue is it identifies the pixels, not actual polygons. So this identifies which pixels are in each region, not the actual polygons. So it's a bit, of a special case, this kind of approach. Now let's look at a more general case. So we notice that the Voronoi cell of a point is the intersection of all the half-planes associated with that point. And here's what we mean by half-plane. Draw a line to some particular neighboring point like this, and look at the perpendicular bisector. So all the points on the left of this red line are closer to this red point than all the points on the right of this red line, which are closer to the blue point, not the red point. How many can see that? Just perpendicular bisector. Pretty straightforward relationship. So the Voronoi cell is on the left of this line. Not any of it is on the right of that line. The Voronoi cell of this red point here. And you do the same thing for other points. So similarly, by the same reasoning, the Voronoi cell associated with this point is on the lower portion of the half plane of this red line, not on the upper portion of the half plane. So as you keep drawing these half planes, those demarcate the boundaries of the Voronoi cell, one boundary at a time. So for this point, you draw this half plane, and the Voronoi cell is basically the intersection of all these half planes, the proper side of all these half planes. And I marked this graphic with this kind of fuzzy area on one side of the line is the correct half plane. The other side is the other half plane that we're not concerned with, that we're not interested in. So the Voronoi cell is simply the intersection of all these half planes, of the perpendicular bisectors between that point and all the other points. And once you keep doing that, very quickly you get the Voronoi cell of that red point. So one more plane intersected, one more half plane intersected all the previous half planes, and voila, you get this Voronoi region right here in red, in solid bold red, and that's the Voronoi cell of that point. Now, why didn't I access or do the same in parallel perpendicular bisector kind of issue with the other points? Well, I did. You do all of them, but I just showed you kind of the relevant ones. Once you do perpendicular bisectors with some of these other ones, like for example this one, the Voronoi cell is on the lower portion of this half plane, but it's already determined by all the other half planes. This is not even affecting the Voronoi cell. You still compute it and intersect it with all the others, but I'm just showing you the ones that don't matter now in dark color, in gray color. Okay, so these don't contribute much to the actual polygon, the convex polygon being the Voronoi cell of this red dot, but they're still there. They're still part of the computation, and you consider all of them, and you end up with this convex polygon. So that's one way of doing it. Now, the question is how fast that is, and it's not very fast. But you can do it for one point, and then you can do it for another point, and then you can do it for a third point, and you build up all these cells, each one being a convex polygon associated with its seed point. And once you do that, you get the entire Voronoi diagram. And then the question is, how long does it take you to intersect these half planes? And there could be n of them for a particular point, because there's n-1 other points, and so there's n-1 half planes, and for every point you have to consider the intersection of n-1 half planes, a linear number of half planes. That's not trivial to do. That's not extremely fast, but you can do it relatively efficiently if you're clever enough, right? So the algorithm here is you have a set of endpoints. You want to put out the Voronoi diagram as the output, and you compute each cell individually, like we just did with this perpendicular bisector business, and there it is animated up here again. And then you want to intersect the n half planes that result from all this perpendicular bisectors. That gives you one Voronoi region. And then you got to repeat that how many times? Linear number of times, n times, because there's n points, and each point needs to, you have to compute the Voronoi cell for each individual point. So the time per cell is, you could do it in quadratic time. Why? Well, you tell me, how can you intersect n half planes in quadratic time pretty straightforwardly based on what we already know and what we've already done? Especially what we've done in the last lecture. It's a hint. The intersection of n half planes. How would you do that? Yeah.
Like we computed the intersection of the convex cells.
Yeah, so a half plane is a convex polygon. How many can see that? It's an unbounded convex polygon, but it's a convex polygon with only one edge. And we already know how to do convex polygon intersection. If you want to intersect convex polygons, we know from the last lecture as you have a subroutine to do that efficiently. By efficiently, we mean linear time. Okay. So you intersect all these half planes. You can intersect them one at a time, and it's linear time with every growing, intersection along the way. So that's n squared if you just do it naively, right? You just call that subroutine n times 1 for every additional half plane. But you don't quite have to do it that naively, right? What you can do is you can intersect the first n over 2 half planes and then the last n over 2 half planes separately, right? And you can do it recursively and do divide and conquer. You can reduce that time to n log n, basically, for one cell intersection if you work at it hard enough. And then for each cell, you want to do it for one cell per point. For each point, you want to find its cell. And the Voronoi diagram is the union of all the cells, so it's n times that. So the naive algorithm will be n cubed. But then you can find the intersection of n half spaces in n log n time, right? And we already showed how to do that with the slab method, these strips and the trapezoids and all that, and stitching together the results. Bottom line is this algorithm eventually gets down to n squared log n to compute the entire Voronoi diagram of endpoints. Now, there's a much more complicated algorithm than this, and that's out of Ian Shamus's thesis in 1977. The guy who founded all computational geometry with his PhD thesis, quite a monumental achievement. He gives an n log n algorithm for the entire Voronoi diagram, not n squared log n or anything else, just n log n total time. And it's basically a divide and conquer like merge sort. It's like merge Voronoi diagram. You compute the Voronoi diagram of 2 halves, then you merge them together and you stitch along the middle. The stitching part is very tricky. The merge part is very tricky in this divide and conquer algorithm that he proposed in the 70s. So tricky that it takes dozens of pages to describe and analyze, and we won't do it here. The book actually describes it, the Proprietà and Shamus computational geometry book. So for extra credit, if you want to take a deeper dive into that algorithm, be my guest. I'll give you extra credit for it, but we won't describe it here. It'll take too long, and the return on the investment is not high enough to discuss it in class. So that's what this is. So it's a divide and conquer, the very complicated merge step. There's a much simpler algorithm, I should qualify by saying it's simpler than this algorithm I just mentioned by Ian Shamus. That's by Steve Fortune back in the 80s. He showed how to compute in n log n time the Voronoi diagram based on parabolas and a sweeping line algorithm. So the sweeping line algorithm basically does this. It sweeps across the point set from left to right or from any other direction. It's really equivalent. And as it's doing so, it's building the Voronoi diagram using parabolas. And again, it's too complicated to explain here, even though it's simpler than the first one. It still works in n log n time. And usually, when you want to compute Voronoi diagrams these days, that's the one you use, actually. Also, it has a nice feature. It generalizes to other objects, not just points. It generalizes to disks and perhaps even other objects like segments. And so the Voronoi diagram could be defined for disks, not just for points, right? The locus of points around the disk closer to that disk than to any other disk. And disks could be of 0 diameter, and that's when they degenerate into a point. But now they don't have to be necessarily of 0 diameter being a point, but they can be an actual disk, a circle. So this algorithm, by fortune, generalizes. Separately, we can prove that Voronoi diagrams require n log n time to compute. That's a lower bound on Voronoi diagrams. So that means that both of these algorithms are optimal, right, because of this theorem. So the corollary is both of these are optimal. N log n time is required, and n log n time is sufficient. So both of these are optimal. Now here is Fortune's algorithm running at 1,000 points. So just so you can see kind of how it works, the full effect. This is actually slowed down. I slowed it down by like an order of magnitude. It's n log n, so over on 1,000 points, it'll be over in less than a second on a typical computer. But I kind of slowed it down to show you how the wavefront of these parabolas kind of helps ascertain and define the Voronoi cells as it sweeps past them, and that's kind of how it works. Again, for extra credit, tell me more about how this works. Maybe analyze it and look at it. There's a wiki page. It's also in some books, and you can take a look at it. And here is Fortune's algorithm computing the Voronoi diagram of 10,000 points, and now it's running in real time. That's roughly about how long it would take to run on 10,000 points. Actually, it might be even faster than that, but this one I didn't slow down the animation artificially. So 10,000 point Voronoi diagram right there. So it is quick. If this was quadratic, it would take many minutes or even hours, possibly, for that many points. Probably minutes. Any questions about any of those things so far? Okay, and so with Voronoi diagrams, once you construct them, you can solve all these other problems. Euclidean minimum spanning trees. You can solve nearest neighbors. You can solve planar subdivision search in a Voronoi diagram, dynamic cases, and many other things. And there's dozens of other problems that you can solve. You can solve the minimum circumscribing circle problem, like what's the minimum size diameter circle that covers the entire point set. Often you want to compute that. That even has applications. Can you think of applications where you want to compute the minimum size circle that covers a bunch of points, that completely encloses a given point set? There's some interesting applications of that. You can imagine there's probably delivery services kind of problems where you want to find, the smallest circle that encloses all your customers, and that circle is your kind of coverage of your service or delivery options. If you're a trucking company or a delivery company, if you deliver pizzas, you want to find out where you have to put your pizza parlor so that you'll be covering all the potential customers in that city that you care to deliver to, and that's probably where you want to put your service center or pizza place or whatever your operation is, somewhere in the middle, around the center of such a circle. Another application is kind of a military, kind of a darker application. You have a bunch of targets you want to take out with one nuke, say, or one large bomb. And the bomb has a certain destructive diameter or destructive radius. And the question is, what's the minimum size bomb you want to put and where do you want to put it to cover all these targets. Your mileage may vary, but that's actually another application of this problem. Anyway, so Voronoi diagrams, very ubiquitous, and now you have, a couple algorithms described and a couple more alluded to, and if you want to read more about it, feel free. Any questions about any of that? Okay. What I'm going to do next, since we have a midterm coming, I'm going to tie up a few loose ends on extra credit problems that were pending from many weeks ago. One such problem is the majority problem. You have n elements, let's say numbers, integers. You have n integers, and with duplicates possible. You have, duplication is allowed, and you want to find the majority element, the element that occurs the greatest number of times, more than half. So majority, we mean half or more. So we don't just want the most commonly occurring element. We want the element that occurs at least half the time or more, if it exists. There may not be a majority, and then you just report that there is none. Or there could be two majorities, right? Half the elements could be x, and the other half of the elements could be y, and now both x and y are technically majorities. They're half or more. So you can have 0 majority, 1 majority, 2 majorities, but obviously not 3 or 4 majorities, because half of them have to be one type or another. How many worked on this problem? Oh, good. How many solved it? And by solving, we mean how fast of an algorithm? Because if you're allowed, yeah, how fast are we? N over 2, yeah, so linear time asymptotically in the number of elements or the number of integers. Because if you're allowed n log n time, you can solve it very easily. If you're allowed n log n time, how would you solve it? One word, sort it, and then you'll know, and then you just scan it and see what the majority is. But linear time, it's not so obvious how to do it in linear time. All right, so how do you do it in linear time? Any thoughts or ideas? Yeah.
You just need to touch half plus ones and it'll get majority, right? So then you just go through n divided by 2 linear time elements, and then if you encounter one more, then and they're all the same, then you found the majority.
Okay, so algorithmically, what do you mean by touch every one? Let's say you start looking at the elements and they're all different than one another. And how do you even know that they're all different? You take an element, it's different than the second, the third is different than the first two. And how do you even know that without comparing them to all these other ones? And that will take time. So how do you avoid all that expenditure of time? Because that can easily pile up and go super linear, above linear, maybe even quadratic if you're not careful. So what do you say? How are we going to achieve linear time on that one?
You have to stay in constant space.
It doesn't have to be constant space, but you have to watch the space consumption so it doesn't grow beyond linear, say. So you won't be able to use a giant hash table or something like that. I know what you're thinking. Big hash table, right? How big will the hash table have to be? The hash table could be 5 times n or 10 times n. That will do it. But how fast is access to the hash table? Worst case. So he's suggesting an algorithm. I'm kind of inferring from what he's saying. Create a hash table, put everything in a hash